Hello everybody. We are still in business of talking about system on chip systems or system on chip chips, and now we are presenting a new manufacturer's chip, which is NXP, or and that system on chip or superset chip is S32G3 Vehicle Network Processor, or VNP, which is delivering high levels of real-time processing, applications processing, network acceleration, hardware security. Also, NXP S32G3 VNP supports CAN communication, link communication, and FlexRay Ethernet networking and communication. Also, gigabit Ethernet interface with hardware acceleration. We will see the different parts which are in charge of Ethernet and uh, hardware accelerations of communication. Also, NXP S32G3 VNP delivering a high level of embedded security and ASIL-D, which is important for the automotive, ASIL-D functional safety capabilities. Uh, in the in automotive industry, it's hard to reach this for some component. It's hard to reach this level, especially if it's so complex. But we can see that this one is completely, let's say, achieving it. Uh, Also, this S32G3 chip supports needs of new vehicle architecture, and it's service oriented for the service oriented gateways. Also, vehicle computers, domain controllers, zonal processors, and also safety processors, and many more other applications. So maybe this one is very interesting and very, let's say, popular application for this component, or as we say, superset chip. In previous cases, when we talked about Versal, which is made from AMD, and also Orange chip, uh, which is made by the NVIDIA, we talk about system on chip, but let's say we can also call this system on chip because it have many features and different kind of features which is similar to those chips which we mentioned also in previous videos. So, but from this, what's mentioned here, and we will see later on other slides, it's more like network-oriented chip, and that Versal and also Orange chip, which is from the one is from the AMD, and second one is from the NVIDIA. They are more like oriented for the IE applications, but also with some communication features. But here we see that CAN, LIN, and FlexRay or Ethernet networking is the main thing which is mentioned for the chip, but we will see the architecture in the later slides. So let's go further. Here's some representation of that architecture for the NXP S32G3 vehicle network processor. We see the sections which are included in architecture. We have memory, which is this is the best option, 20 megabytes system SRAM, standby SRAM. Also, this is probably some port for the or communication for the DRAM. I doubt that's directly included on chip. Maybe it's just the interface for that. Also, NOR flash memory and NAND flash memory. We will see this stuff in details. I'm not sure for this one, DDR or DRAM, is it directly on the chip, but we will check later. Also system FCCU, I didn't found in particular what does it means. Also PLL, which is phase locked loops, which is which is very important for the giving the clock for the different kind of, let's say, frequencies for the cores which we need. We have two safe DMA controllers, direct memory access controllers, debug unit and trace, and 16 times XRDC domains. We will see later what does it means. We can go on one page further to check what does this exactly means. It means extended resource domain control, and it's 16 isolation domains. It's part of the system, yes. So we can go back to this slide. Also, we have security section on this chip, which is HSI, or hardware security engine. We have here serial communication, which includes 6 SPIs, which is very, very rich, we can say. Also 5 times I2C ports, or possibility to link with 5 I2C devices. Also 4 CAN FD devices. 3 LIN or UART devices. Probably we can use here one or another, which is probably in the sense of 5 volts on the output and 5 volts on the input, TX and RX. Also FlexRay, we say something that that it's linked to the Ethernet, also USB, which is 2.0. We see that USB link is not very fast here in this case, but also we can see that this is almost similar to the small computer or system on chip. Also two interfaces for the PCI communication, which is 3.0, which is pretty much, let's say, good. 3.0 generation is, let's say, in the middle. Most advanced today is 5 or 6, but it's for the very high speed GPU, CPU communications in desktops and laptops and so on. Also, it has 12 Watchdog timers. Watchdog timer is related with the and refreshing Watchdog of the Watchdog timer is related to see our cores working properly. So if we have 12 cores, we have 12 Watchdog timers, which are monitoring and waiting for the some refreshing for this from this cores. So that's why 12 cores, 12 Watchdog timers. 13 times system timer. I'm not sure for the application of this. Also 12 flex timer, maybe for this FlexRay or whatever. It's some kind of clocking systems. And we have two SAR ADCs, analog digital converters, which is 12 bit. Also type of ADC is successive approximation register analog to digital converter. So that's the type which is also usual for the use in microcontrollers, which I let's say saw on in automotive industry. So once again, two two ADCs with 6 channels, probably with some kind of multiplexing and selecting the channel to be put on ADC. Also, both of them are 12-bit. That multiplexing is actually allowing us to have, let's say, virtual analog to digital converters. It's like we have more because we can multiplex the channel which we want to proceed on the analog to digital converter. Also, we see here also in the processor section that we have ARM Cortex M7 cores, and we have 4 of them. We usually see them in microcontroller applications or inside the microcontrollers. One or two of them is common for the microcontroller, but we have here 4 of them. Also, it's mentioned that they have I cache and D cache. What is I cache? It's instruction cache, separated instruction cache from data cache, and that's also usual application in microcontrollers which are related, let's say, which have applications also in automotive industry. So that's the main thing about I cache and D cache, to have complete comprehension what is that. So instruction cache and the data cache, and we can see that it's separated. They have separate space for storing the instructions and the data on which these instructions are done. Also, we see here that we have more complex cores, 8 of them, and they are ARM Cortex A52 in 2 clusters. Also have L1 cache and I cache and D cache. L1, L2, L3 caches are mostly, we saw that in processors and GPUs. We can say that this one is more like a processor section, and this one is more like microcontroller section. So we have in one chip, we have microcontroller and microprocessor. So to see how rich this, let's say, superset with the resources here. Also, we mentioned this timers and ADCs, also mentioned the communication, 1 GB Ethernet, and also we have Ethernet networks, and this is all one big part which is called network acceleration, and we mentioned that in previous slide, that this is one of the main topics for this let's say system on chip. And also we see here that we have 16 CAN-FD ports or interfaces. I don't know is it these are the separate or not, but probably yes, but this is different section which is network oriented, but this is like common interface. But we will see later in the documentation. Also flexible buffers, 4 lanes. We have here 3 lanes, yes, 4 SPIs. Or here is 6 XPIs. So probably this is some advanced section for the communication and communication oriented only sections, security offload, global timestamping. I'm not sure what does this mean. We will see later. Also, in this network acceleration section, we have automotive networks. So this part of this network acceleration section is oriented for the automotive applications probably, and this is meant to be used in automotive industry. So we see here 16 CAN FDs, which is very important in sense of um, resources for the CAN communication. And that's why this device is used mostly like some kind of gateway, which we mentioned in the previous slide, service-oriented gateways, yes. And also this section is Ethernet network, so this is more for CANs, LINs, SPIs, and this is for the like classical Ethernet network section, which have, let's say, we see here 2.5 gigabit Ethernet interfaces. So also it's very rich for the Ethernet applications only, and yes, we have packet forwarding engine, which we also mentioned, I think, maybe here or maybe on the next slide, but we will tell about this more later. Anyway, network acceleration is like providing to this device to behave like interconnection and gateway between different sources which need to communicate with each other. So in that sense, that's why they mentioned gateway. So different type of communication links or interfaces, which is which sources for that, which is very rich. We see 16 CAN FD, which is a very fast CAN interface, 4 LINs, SPIs. So this can be, let's say, some place which can provide interconnection of the different part of the, for example, some car system, and this vehicle network processor VNP S32G3 is actually mostly mentioned for these interconnections between different parts of the let's say car system or any kind of complex system which needs to which have a different kind of communication interfaces included. And we conclude why, where is the origin for that? Where is the origin for that name VNP, Vehicle Network Processor? Also, let's say some resources: 8 ARM Cortex A53 cores with the ARM Neon technology organized in 2 clusters of 4 cores with the optional cluster lockstep for applications and services. We will see later what does it mean. Also 4 ARM Cortex M7 dual core lockstep DCLS complexes. We told that this is more like a processor with ARM architecture, and this is more like a microcontroller alike cores. Also, this version, I didn't mention exact version, but this we pick up version with most this DRAM, not DRAM, SRAM, sorry, and it's 20 megabyte on-chip system. Probably it's for the all cores and for storing and buffering the memory for to be used in for this or this course. Also LLCA, low latency communication engine for automotive networks acceleration for real-time applications. So I think this real-time application is much more on the lower level, and it's more connected with this ARM Cortex M7, but we will see further in the documentation. PFA, packet forwarding engine. This is part of the communication. Let's go back to this slide. Yes, packet forwarding engine. It's like for the Ethernet networks, which are part of this section of this chip. For Ethernet networks, yes, like we mentioned, with 3 ports supporting 2.5 gigabit per second, marked with violet color on the diagram. This is my note to show you exactly where is that. So this is Ethernet network, which is part of network acceleration. So we want to increase the capabilities for the network interconnections with this chip, and this is section especially designed for that with this 2.5 gigabit Ethernet ports or interfaces. Also, HSI hardware security engine for secure boot and accelerated security services. It said something, but not too much, like what this HSA section is for. We mentioned it previously on the when we talk on this slide. We see what is inside of it. Asymmetric hardware accelerators, symmetric hardware accelerators, secure memory, random number generators. Yes, this is probably very important. This is maybe encryption, symmetric keys, asymmetric keys, maybe some crypto keys generator or something like that, but we will see in the further let's say further explanation of this system on chip. Let's see further what's happening with our resources. XRDC, extend resource domain control, 16 isolate domains, and this is part of the system. Where was it? Yes, this is the system, and that's this. Also, this is operating temperature, operating range for this system on chip. We see here, I mentioned here, which is the max frequency for the working for M7 cores is 400 MHz. ARM Cortex A53, 1300 MHz. Like we said, this is like more microcontroller cores, and this is like microprocessor cores. Size of the L1 cache, 32 kilobytes of eCache, and the same thing for the data cache. Also, this is for the Cortex A53 core. L2 cache, it's for the clusters, and it's 1 megabyte per cluster core. And also, I explain here that we have a successive approximation register analog to digital converter, ADC, so which type is, and it's a common type for the application automotive industry and for the microcontrollers, and usually inside different kind of microcontrollers which are applied in automotive industry. So let's go further. Can we see something more interesting? Yes, PLL. We see 5 PLLs. Also, digital input instances. Yes. Blah blah blah. Phase lock loop is this PLL. It's yes, for the generating different kind of frequencies for the different kind of cores. We will see further. This is just for the mentioning and how many of them is inside. And this is DRAM. It can be up to 4 gigabytes. which probably can be connected, but I doubt that it's inside of the chip. I'm not so familiar, but we will see in further, let's say, videos what's going on with this. So obviously that it has DDR3L and LPDDR4, maybe one or another, but I'm not sure. We will check later what's happening with that DRAM. So I think this is enough for this video, and we will see and discuss more about the resources and architecture of this vehicle network processor. We see the main application. It's slightly a little bit different from previous mentioned chips, which are more oriented, let's say, on the IE and AI, and also adaptive logic, which have programmable logic in case of Versal. And when we get familiar with architecture of all these kinds of chips, we will make some comparison and see in which sense one or another chip is better than those other tools. Maybe include some also counterparts from the different manufacturers. The idea is to have good information of all platforms which can be used tomorrow in different applications. So greetings for now, and I hope that you enjoyed and that I was pretty much understandable in these topics. Goodbye.